Hi, I'm Paul from Test Data Services, and this video is the 10th in a series of video summaries showing how to do performance engineering and performance tuning in a real-life scenario with a real app. In this video, we're going to close off cycle 2 and show you the improvements that were made, and better still, how we did it. So I relied on X-Ray extensively for this. So this is an example of an X-Ray screenshot from, or it's actually live X-Ray, from a test I ran earlier, which is in this video. And you can see here that this particular call has some slow responses. We can zoom in on those slow responses. And if we do that, we can actually get visibility into what's slow, which is great. Like in this case, this update transaction. But the best thing is that those transactions are actually reflected in my LoadRunner screen while the test is running. So I'm going to show you in this video how I've integrated LoadRunner with X-Ray so that while a test is running, I use the appropriate API endpoints to actually fetch X-ray summaries and the actual traces themselves into, or the data from them, into LoadRunner. So you can use the chapters down the bottom to scroll through and like fast forward over the bits you're not interested in. I'm going to do a presentation first on what's been achieved, and then I'm going to show you a few tests in the end and the analysis that's actually the focus of this screen. So this is a quick walkthrough of the main components of the Cycle 2 performance engineering. So we achieved several things. We achieved enhancements to scripts that gave us much better insight into what's going on. And we did that with integration of LoadRunner to CloudWatch and integration of LoadRunner with X-Ray. So we dynamically fetch data from CloudWatch, whether it's anything from CloudWatch. In fact, I fetched many things, including like concurrent lambdas running for individuals, and also aggregated them so I could get a view of what's the concurrent lambdas for a set of transactions. I developed a better test, therefore, that provided a much better real-time insight into what's going on. So unlike a test that you would automate and just run every night or every day or after a change is committed to your system, if you're doing a performance tuning cycle, you often watch the test while it's running. And if you're doing that, it's awesome if you get real-time visibility into instrumentation. So we also achieved in this cycle substantial improvement to performance and capacity. In the cycle 1, when we ran a concurrency test with 10 users, full speed, no think time, no iteration pacing, which is useful only for concurrency, it's not best practice for normal testing, we were able to get a 10-fold increase when we stepped up from 10 to 100. Our response times didn't change. When we stepped up from 100 to 1,000 concurrent users, we only got a 4-fold increase in transactions instead of a 10. And that's because our response times degraded. But the good thing was, in this situation, we still had a pretty low error rate of 1 error per 125,000 transactions. In this cycle, I've just run a 10-user test, a 100-user test, and a 1,000-user test. And these are the 2-minute stats for the peak 2 minutes of those three tests. And the summary of that is much better transaction rates for the 10, 100, and 1,000 users. But you can see that when we went from 10 to 100, we still maintained our 10-fold increase, which is really good. We still maintained our response times. But when we went from 100 users to 1,000, we got about a 9.3-fold increase in transactions. Not quite 10, but pretty close. Also, our error rate was 1 error per 275,000 transactions, which is pretty awesome. Now, the main performance improvements we were able to achieve was with DynamoDB changes, and we focused on them because of what X-Ray showed us. So in this case, we've got a function, a Lambda function that's come from API Gateway, so from our test, that took 2.3 seconds. And you can see the get items down here are sequential in nature, and we have one whopping great big put item. So one of the things we're able to do is consolidate a lot of those gets into batch gets and also batch writes. So when we do this, they're much faster because we're running them concurrently. But instead of doing like 3 concurrent DynamoDB calls that you just let run, like with Node.js, it's very good at doing concurrent I/O, but you still would have the overhead of firing up DynamoDB components in the background. Whereas if you do a batch one and you do 3 updates, you only have that overhead once. So that's a pretty useful thing. We managed to integrate X-Ray in with LoadRunner to allow us to get real-time visibility into what X-Ray is telling us. So in X-Ray's instrumentation while a test is running. So to do that, I developed an API gateway endpoint with Lambda code behind it that did some X-Ray calls. So the X-Ray calls, I'll explain this first. So we had a single VUgen script, which was configured to be able, with a parameter file, to be able to make those calls to API gateway to fetch that data. It defined in that config script the segments to monitor, the reporting threshold, and a transaction name prefix, so that it would actually create transactions in the load testing scenario. So each result from each call generates a custom transaction, and any response time spikes caused by a burst of X-ray detail appear as discrete transactions in the LoadRunner console and the results. This is what the Lambda code looked like to do the X-ray fetch. That's the whole thing. It's not very much. This is looking at it in a bit more detail. So what we're really doing in here is we're doing a get trace summaries. And the script, the way it's set up, is it makes a call every second to this. And it looks back at a number of seconds for a 1 second window. So like, for instance, 30 seconds ago. So every second it looks back 30 seconds ago to find out what traces have been retrieved. Sorry, what traces are there. We get a summary of them. And that gives us a list of IDs. And then for everything in that list of IDs, we go through and we basically filter out the ones that we care about if it's over a threshold that we're interested in. And we actually even pluck out the segments we're interested in. So when you get a trace, there might be 20 segments in there. We might only focus on the DynamoDB ones, or we can actually separate them out. So this is letting me do that. The VUgen code to achieve the integration is here. So it's one simple script and with a parameter file, and that parameter file includes like a look back seconds, a window, segment name, and so on. And it makes this call, and whenever the call comes back, it takes every response in the JSON data that comes back, and it converts it into a transaction with this lrset transaction, which is pretty good. So the benefits and issues of this X-Ray integration, it's wonderful being able to see and save the application instrumentation data as it becomes available, because it really simplifies the whole test execution and performance engineering, troubleshooting, tuning process. However, if you'd set to look back at 20 seconds, I'm actually moving more toward 30 seconds now, you'd have a delay of that 20 or 30 seconds between the actual traces being generated or the underlying transactions executing, and you seeing them. So when you want to correlate, that's not so good. So if you're having a gradual ramp up in response time, this is fine because it'll just be delayed by 30 seconds. If you had spikes, then your spikes will be out of alignment. Worth noting, but really for the purpose of getting visibility, I'd rather have spikes that are not quite aligned, but I can see them and understand what's going on, than not having anything. Very long running transactions won't be caught. So let's imagine you've got a transaction that took a minute to run and you're only looking back 30 seconds. Well, you're never going to see it because the trace won't be written until the transaction's done. So you'll have issues if you do that. And like I said, the transactions don't line up exactly. So things to watch out for. Ensure that the threshold for X-ray monitoring is set just to catch the ones that you want to catch. And you might want to have a second threshold for very large transactions. Ensure your load generators are always the same class. If you ran a whole lot of tests with, say, T3 type instances on AWS EC2, you don't want to then run some other tests with C5s. I prefer C5s because the CPUs are a bit faster. They're a little bit more expensive and they're more reliable than T3 for sure, like from a performance perspective. And also be sure to spread out the load generators evenly. If you've only got 5 or 10 load generators, it doesn't matter. But for some of these tests, I was running like 100 load generators. Then you want them to be spread out. Now, the way I spread them out is I showed you in an earlier video in this series a simple PowerShell script that launched a bunch of load generators. Well, this is the more sophisticated version where I actually say how many instances I want in each of the AZs, AZ A, B, and C. And then I actually create, I do this new instance, and the code, when it runs, will actually produce all these load generators. Let me connect to them. Oh, the other nice thing though, is I actually put a starting number in. So I've got starting generator number 1001. If I've created like this, that's 78, right? 26 times 3. If I create those, then it'll start the counting at that number. So if I wanted to add another 50 load generators to do some more, like I'm up to 1103 here, I can actually just change that starting number and have more, which is pretty good. So in this session, we're actually going to rerun the 10, 100, and 1,000 concurrent user tests, and we're going to run a large load test with the purpose of bringing on some throttling, some basically hot segment throttling, and then we will do some analysis on that. So now to the 10 user test. Well, this is the 10 user test, the 10 user concurrency test with no think time, no iteration pacing. And what we're doing, plus we've got an extra 3 users doing X-Ray fetching, and we've got 1 user doing AWS CloudWatch fetching. So if I switch across to the transactions per second graph, I've set this to a scale of its whole scenario. I'll change it to 60 seconds. So that I can actually look at the transactions per second over a minute. I'll read the average off the screen here, and I'll put those numbers into the spreadsheet so I can keep track of it just for fun. So we've got transactions here as we're doing refresh tokens. I can probably pretty well read that right now. I don't really need the average, but let's wait for the average. So let's look at the test. We're going to run for 3 minutes, so I'll be able to do post-test analysis and confirm what the average is over say 2 of those 3 minutes. I don't need to run a really long test. It's just not worth it for these results. Okay, so I've got enough data there now. So the authorized transaction, which is after we've created the user, we're averaging 37. So let's put that in. Authorize refresh 37. And this one is authorize. So it's the login part before doing a whole lot of refreshes. And it is, oops, what was it? 7.7. Let's call it 8. And the sign up authorize is 1, and the token exchange is 1. So that's good to know. So 1 and 1. So that means we're doing about 47 OpenID Connect calls per second with 10 users. So we're expecting to see these numbers multiply by 10 when we do 100 users and by 100 when we do 1,000 users. If our scalability now in the current state after cycle 2 performance and tuning has done its thing. Okay, so next one is the 100 user test. Okay, now this is the 100 user test. No iteration pacing, no think time. Our response times are pretty stable. Let's go and have a look at transactions per second passed. And just so you can see, we've just hit the peak load a few seconds ago. We're heading toward the first minute. So as we're heading toward that first minute, let's pull up that spreadsheet and let's update these numbers. So the top one here is what we'll focus on first. So this is refresh tokens. It's looking like it's about 370 something, the average. So we'll see that average stabilize out. 342, Yes, it's going to average at close to 380. 362. We need one more sample when this over here is no longer sort of during the ramp up stage. Okay, 375. I'd call that 375. Let's go in here and type in. So 375 instead of 37. That's a good start. Now authorizers. We're doing 74. That looks pretty good too. And then the sign up, authorize and sign up token exchange. Token exchange, we got 10, that's pretty close to 10, 9.9 and 9.9. So that's great. So far so good. So we went from 10 users to 100 users, and we've seen pretty well a 10-fold increase, which is what we want to see. And the next one is 1,000. So I'll show you that next. Okay, now we're running at 1,000 concurrent users, no iteration pacing, no think time, and our response times have stabilized. Transactions per second has stabilized. Let's change this graph to show just the last 60 seconds so we can get an average reading. So we're nearly there. Let's look at refresh token and pull up our spreadsheet. So we're at 35.75. That's probably a good number, 35.75. And then this one down here is 715 for the token exchange on authorize. It's a little bit less, but pretty close to 10 times still. And then for sign up, we've got token exchange at 98 and authorize at 98. That's pretty good. So very close to a 10 times increase. Whereas last time we only had about a 4 times increase. Now we have a 10 times increase, pretty close to. So that's a really good indication that the changes that we've implemented in cycle 2 have really led to an improvement in scalability. So this test is going to run for another minute or so. I'm going to pause this now and show you something. So I'm going to let it run for a bit longer than normal. I'm going to go to AWS. All right, so we're currently seeing 1109 requests per second come in, and our sampling rate is 16.6%. I didn't turn it down. So if I now change this to 1.6%, which is what I would normally do, let's see if that alters our performance at all, which I don't think it really will. So back to here. So I haven't seen what looks like a change yet. It doesn't usually take very long for the sampling rate to change. It usually takes about 35 seconds, I've noticed. So far, so good. So changing the sampling by a factor of 10 from 1.6 to 16% or vice versa looks like it's made no difference, which is great. It's fantastic, really. I've gone all the way to 100%, which is fun if you want to get every sample. So it really scales well, X-Ray does. I'm going to stop this test now. Okay, next will be 15,000 user test, or maybe more, we'll see. Okay, so now running a 15,000 user test, or close to 15,000, and I'm ramping up, and I've set up the script to cause DynamoDB contention, with a hotkey. So I'm using half of the authorized transactions we'll be focusing on one particular OpenID Connect client ID. So I'm ramping up at the moment. While it's ramping up, I want to show you the way I'm using the X-Ray integration, which is pretty important. So I've got a script. The script has a parameter file in it. The parameter file in this case has 3 lines, which means I've got 3 scripts running. It will sort of partition off the work accordingly. I've got a look back of 30 seconds. So what that means is it's going to look back at the current time, subtract 30 seconds. So 30 seconds in the past, and it's going to look at 1 whole second only. It's going to look for all DynamoDB segments within any traces that match, in this case, an authorization call or a token call or a push identity call. So in the actual configuration file, I've specified what the actual transaction or trace name would be that I'm, the entry point would be that I'm tracking. And now if you make this number too small, you have 2 issues. The look back time. You want to make it small because you want your traces to appear in your load test console as soon as possible when you've actually got some contention or some slowdown. But let's imagine that it takes 20 seconds for Amazon to give you the traces and make them available. If your response time was, say, 10 seconds for a trace, then it means that your trace is going to be outside of the window. So if I'm looking at transactions that can slow down by up to 10 seconds, and I'm expecting most traces will be retrieved within 20 seconds, then I've set my look back time at 30 seconds, which I think works pretty well. I've had issues where I'm setting it at only 20 seconds. Now you can see here it's flicking on the screen. It's got 4 traces just then. You saw that? It said 4. So that means the token call returned some data. If the token call returns some data, then it's another 4 there. It means that we've got some extra transactions now to look at. So this is the transaction response time. So they're going to appear here. And if we look at the transactions passed, we can actually see how many we've had. So we've had 3 lots of 4, which is 12. So these are, I've got the prefix is trace token to give me an idea that it's the token call, which is the one that we're looking at, the DynamoDB, and I've got DB batch get item, DB batch write item. So these do multiple gets or multiple writes. When the writes could be puts or deletes, and then we've got gets and we've got queries. So in this case, none of them are particularly slow. If we just focused only on those, if I just highlight them, we can see we haven't got any terrible response times yet. So we're not at a point with significant contention. If I look at the current X-Ray map, refresh the map, and we can see that everything's fine. We have no errors in the last minute. And we can see a decent rate of transactions here. So there's the authorized call. The token call would be, so this is the token call. We have a few errors now. And our distribution of response times, we can see we've had one that's more than a second. So we should have caught that in our load test. And I think we did. So that 1 second one will be this one here. So it's pretty cool that we can actually see that as it's going. And also it's nice that we actually get to have this data persisted in our result set. Okay, so main thing is we can see this. I'll show you in the analysis what it looks like, which I think will be a good way to go. But you've actually seen that, and you can see in here that we've actually got some contention. So I'll join you again soon. So before I dig into the analysis, I just wanted to revisit the actual integration with X-Ray because I think it's pretty cool. I'm just going to start up a small test so you can see. And now this is the script that I showed you earlier in the video. That's what the script looks like. If I push run now, it won't do very much because I am not running any activity. Now the parameters that I've set up, I've got 3 of them here, a bit small to read. But if I open up with Notepad, we can see that the first line's what I'm going to show you now. It's for authorizations. It's looking for an entry point of testdataservices.com.au v001f OIDC authorize, and it's only going to extract out the DynamoDB segments within that, and it's going to do it for all segments for all traces that have a total duration of more than 0.1 second, and it's going to look for a 1 second window back 30 seconds. So we've been running activity now for more than 30 seconds, and we can see that every second we're actually looking at how many traces. It's generated 105, 98, 98, 98, 98, 105, 105, 112, 126. So this is actually capable of like 1,000 a second. Now, the way I've set the tracing up just now is I've asked it to do 100%. So we've got 71 traces there. Now, when I said trace transactions, if we have one trace that satisfies the criteria, we'll generate a separate transaction for every relevant segment. So if there were 4 DynamoDB calls, 4 segments, then we'll do 4 transactions. That's why you'll often see larger numbers here than is actually the number of traces. So then if we look at the transactions per second, we can see that we're doing like 15 a second of the DynamoDB batch get item. So that's a segment within X-Ray that points to a single call to batch get item, which actually gets 3 different values from DynamoDB from different tables. Whereas this batch write, that usually does 2 inserts and 1 delete, for example. But we can see these rates here. The users one, we've got twice the rate on users because it's called from multiple scripts. But we're seeing it just here. So the nice thing is that if we now have that, then we can actually see those response times as transactions in real time, which is really great. So if I just grab, if I sort it first so we can see it a bit easier, they all start with the word trace and then the appropriate prefix. If I just show only these, we can see that there. Now, when we see that we're getting like tens per second of these, as long as we have our sampling rate set appropriately, then we're going to be good to go for catching live instrumentation that's just delayed by 30 seconds in this case. 20 seconds works fine for some things. If you're getting large transaction response times like 10 seconds, then you probably need to have it at least at 30, maybe 35 or 40 seconds. Just need to play with it a bit. But this works great. I've used it and it's fantastic. So that's that. So now to look at the analysis. And I don't think I need to go through this with you anymore. I showed you in the earlier introduction what that looks like. So this now is a few minutes from the 15,000 user test that I ran earlier. And we can see that we started getting little spikes and then the spikes got bigger and bigger and bigger. Now this purple line here is the authorized call, the actual HTTP request for authorize. And these ones here are the trace transactions. So this one is the trace transaction from the push identity call for update item. So the issue was that the authorizations were happening once per iteration, but the writing to the user table, the ODBC user table, happens more frequently from two different directions, if you like. So because I have a hotkey on purpose, I deliberately made it so I'd have a hotkey with the data array selected to use. The first thing that's affected is this. So when we look at this and we're getting these spikes getting bigger and bigger, and our response time for push existing user ID is starting to grow, we're noticing these high responses. So that's a clue straight away. You just mouse over it and you'll see straight away it says it's the push identity one, DynamoDB update item, and it even tells you the table. It's TD001F OADC users. So that's enough to know what's going on. Now to show you what that looked like though when I was running that test. So this is the time in local time in Melbourne. We are UTC minus 10. So if I was to go back to here and UTC minus 10, it was 10 a.m., right? 10:13 a.m. So I just take 10 off that, and I can see that I'm looking at the 1 minute. I'll go back to service map so I can specify. I'm looking at the 1 minute from 11 minutes past. So the minute I'm looking at is this minute here, and this is the performance in that 1 minute. If I was to switch this to say 3, I get worse performance then, right? So now I'll actually see more contention, quite a lot more than the previous one. So you can see these the purple here. So requests to push identity is the one we're looking at. It goes to push identity lambda function, and we can look at that actual instance. There was 1,100 traces per minute inbound of that, and there was 6,300 requests per minute that were traced into here. And if we look at, and that was being sampled at 1.66%, which is a 60th. So we're actually doing 6,000 requests per second. And I distributed a fair bit of them over multiple OpenID Connect client IDs, but I deliberately skewed it so that I would have a cluster and I would have a hotkey. So let's look at this now. And if we've clicked on that one, and we can see this is the response time distribution for these slow transactions. And we can see here we have some that are throttled. So if I click on throttle and then click analyze, we're only going to see the throttled ones. So we'll do that first. And the response times are sometimes quick, but there's still throttling there. And when we look at it, we'll see an error, right? It gave up after 1.3 seconds. But not all of them give you an error or do that. So if I go back, and if I don't click on throttle here, but I just look at transactions that took, say between 1 and 5 seconds, analyze traces, then we can see the distribution here, and we can get a sense of what's going on. Now the user agent, I embedded in the user agent, as you can see in a previous video, the client ID I'm using. So I'm using 40 different client IDs, but all of these requests, these 61 traces, have the same client ID. 100% of them do. That really gives me a good strong clue that the problem I'm facing with this throttling, this contention, is related to this client ID. If it was distributed, 3% here and 2% there, and a whole smattering of them, then it wouldn't be the particular OIDC client ID at fault. So now we can look at any of these. Let's just randomly choose one. Now in this case, we've got a 4.4 second response time. We've got a few milliseconds here for these ones, and then we've got this DynamoDB call to update item OIDC users, which is the same as this one, right? It's the update item OIDC users. If I just, I gotta click on it, sorry. There we go. Update item OIDC users. So In here, what we can do though, it's a bit more detail, I couldn't put this into LoadRunner easily, is we can actually look at the resources, and we can see that in this case there was 7 retries, but it succeeded. So it passed, it didn't fail, but it did seven bites at the cherry before it succeeded. So what I've tried to show you here is that the data that's showing up in LoadRunner is the same as the data that's in the X-Ray console, which is really great. That it's really good to go in. You get wonderful visibility using the console. But let's imagine you weren't allowed to have access to the console and they didn't want to give you much privilege, or there was just difficulties. If your test is able to make a call that is protected and is able to fetch that data, like what I've done, then all of your tests, whenever they run, can access it. You don't need to log in and see anything on the X-Ray console. You can just see it right here, right now. And also when you're testing later on and you go back and you want to review, so when you're analyzing later on, you want to review, then you can actually do that, and you'll see these artifacts here left over from that root cause, which was that slow transaction. So I think I've given enough of a summary. I don't think I've left anything off. After I've pushed stop and published, I'll realize I might do a follow-up video if necessary. But I hope you've enjoyed these series of videos showing performance engineering with a real-life example, and digging in and documenting them with video summaries, which I think is a great way to be able to leave a trail of information for future team members who join your team who want to come up to speed quick. There's nothing quite like watching a video of what someone did to get an understanding of it. All the best. Have a great day.